Okay, we're surely going to get some more people filtering in the next few minutes, but just so that we don't start from behind, I think we should go ahead and get started here. Hello, everybody, and welcome. Thank you for joining us today at this GEER webinar. If it's your first time with us, or if you haven't heard of GEER before, GEER stands for the Geotechnical Extreme Event Reconnaissance Association. My name is Elliot Nichols. I'm a PhD student and student recorder for the GEER Association and for Dr. Frost, the director of GEER. To start, GEER would not exist without the support of the National Science Foundation and the NSF program manager, Giovanni Biscontin, who has been a major help and asset to GEER over the years. So want to thank NSF to start here. GEER's membership is composed primarily of geotechnical engineers and earth scientists from all different sectors, academia, industry, government, and that membership is who makes up our field teams. And I'm happy today to introduce some of our field team here from one of our events. GEER responds to earthquakes, hurricanes, wildfires, and other sorts of events. But today's event that we're going to talk about is the 2021 Western European flooding. The response came in two phases, the first of which came a few weeks after the event in early August 2021, and the second phase came about 7 months later in March 2022. The webinar today is mostly going to cover the initial phase 1 response, but you can, of course, feel free to ask questions about phase 1 and phase 2, which will be covered a little bit. I should also mention that the full 260-page GEER report is posted freely online at GEER's website, and I'll include a link to that in the chat below. I'm very pleased to introduce our 4 wonderful speakers today who are part of our GEER field team. We have our 2 co-team leads, Professor Anne Lemnitzer from UC Irvine and Professor Nina Stark from Virginia Tech, whose German connections and fluency over there made the entire trip possible to start. And then we also have 2 more members, the phase 2 team lead, Professor Mike Gardner from the University of Nevada-Reno, and Dr. Michael George from longtime GEER partner and collaborator, BGC Engineering. So without taking up too much time, and without further ado, I think, team, you can take it away and start your presentation whenever you're ready.
Thank you very much, Elliot, for the kind introduction, and also welcome from the team. And on behalf of Nina and myself, welcome to this seminar. We're very grateful again to GEER for supporting us in this deployment, and also for NSF, not only for funding GEER and the many valuable reconnaissance missions over the year, but also for the additional support that we've received after to go back and collect additional data. As a result, whatever we present today are our own observations and data. They don't necessarily reflect GEER or NSF. So I just wanted to put that disclaimer out, and we just hope that you can enjoy our findings, observations, and take away valuable lessons learned towards a more resilient built and natural environment. As Elliot mentioned, we had a very multidisciplinary and multi-international reconnaissance team. Nina and I are both of German origin, which made it much easier to maneuver and assemble collaborators within the European countries. Besides Dr. Gardner and Dr. George and Elliot joining us from the United States, Professor Schüttrumpf and Stamm joined immediately the team, as well as Jeremias, a graduate student, and they're all still working on us, evaluating the data. They returned for a phase 2, and we established a very good collaboration with our European colleagues. In the Netherlands and Belgium, we had the 2 members at the top assemble a team, and they really took away the lead. It's a group of academics and consultants which arranged for meetings and managed access, as well as helped establishing those sections for those 2 countries. So today's talk will only cover a very small amount of observations that we gathered, just because the area that was damaged was so large and the damage was so big in magnitude. So after this brief welcome, I will start by introducing the flood and give some background information on how it came to this extent of damage, followed by some general observations from the Erft River and the Aar River. And then Dr. George will give us 2 case studies that go into more detail about a dam, a successful dam story, as well as the Altenaar tunnel entrance and exit area. Dr. Gardner will show some innovative measuring techniques and data collection methods and interpretation approaches of what we deployed there to make the most out of this reconnaissance data collection. And then Nina will really highlight this unique approach to a phase 2 return and the valuable data we were able to collect there. So since we were already introduced, I'm not going to go over this again, but this slide always makes us feel so much better. This is us in some younger years. but we are still trying to hold up our same expertise with a very different background. Mike from a geological perspective, the other Mike coming with the focus on dams, river engineering, water resources, Nina in coastal and marine geotechnics, and I myself in the interface of geo-structural performance behavior. Now, the 2021 year was really a year that was hit with many catastrophic events. This is a worldwide map established by Munich Re, a European reinsurance company that is pretty much the back insurer for the regular insurance that you purchase against natural hazards. All these small dots are minor or medium natural hazards events, and those big ones are really the most severe ones in 2021 with a huge loss in infrastructure or built environment, as well as fatalities. So when we look at those top 7 costliest natural disasters worldwide in 2021, we see that this European flooding really ranked second out of everything else in the world. First, it was Hurricane Ida with $65 billion of total damage and losses. And the flooding in Europe, the sum of all 3 countries combined is about 54 billion of damage. 13 were insured damage. The US in total took actually away the highest disaster losses with a cumulative sum of $145 billion. And now when we look at purely European ground and look at the flood events in the last 30 plus years, we see that the 2021 flood was also really the heaviest in terms of the death tolls. 238 is more than 3 times of whatever a flood event has cost in the last 3 decades. And the same is reflected in the cost amount. We see here with the $54 billion that I just mentioned, the 2021 flood way surpassed any of the floods since the early 90s. Now, the question may arise, why is this so expensive? Why was this so costly? And the reason is really that the damage happened in very well established and advanced engineered areas with good infrastructure, expensive construction. And once this is gone, there's a lot of financial loss associated with infrastructure, residential and industrial damage. And in this map, we see this area that covers Germany, Luxembourg, Belgium, and the outside edge of the Netherlands. Now, many people asked afterwards, why was this flood so devastating? And especially in those areas like the Ahr Valley or other regions along the Erft and Ahr rivers, it was really a combination of very unfortunate but common circumstances. It was the local geological condition, a pre-flood soil saturation, and an extreme precipitation. And so when we look, for instance, the Erft River here, that's shown on the top photo, and I hope you can see my mouse pointing out the river, as well as the River Ahr, are both located in valley areas. And if we look at the elevation profile for these cross sections outlined on the left, we see that the rivers respectively lay at the lowest elevations and are surrounded by hills, mountains, occasionally with slopes of up to 55% inclination. So they don't only have the precipitation of the area, also the runoff of all the surrounding area and whatever comes from upstream. So the accumulation of water and likewise damage that was caused in these valleys was enormous. As a result of this mountain geology, there's also very little soil coverage. And since it has been raining for several days before the major flood event already, the water storage capacity shown in those 2 graphs was very low. We were at the 0 to 10 millimeter capacity. This is the region that we ended up visiting, and so it was already at critical conditions before. Now, the warnings went out early. We knew that the low pressure system Bernd is coming in from the south of Europe into Central Europe, especially Germany. Initial predictions set a cumulative precipitation of about 100 to 150 millimeters occasionally, or very specifically to 200. Now, as the days Sunday, Monday, Tuesday progressed, on Tuesday, this whole map took a little bit of a different shape. Now, really, the country was alarmed, huge amounts of precipitation expected. This number was actually exceeded in some region. It went up to 240 or 248, even in Belgium. And now on Wednesday morning, really the first flash flooding was issued. And you can see the blue area expand in size and width, and flash flooding for a majority of the regions in Germany, Luxembourg, and Belgium was issued. Still, not all people evacuated. Many people thought that it's going to be a similar situation to the 2016 flood event, but on Thursday morning, this little river here, this is the Ahr River in Altena, took a totally different turn, and it turned into a massive amount of a river stream with flooding all the plains around it that was available. The flow velocities were relatively high, well, much higher than experienced before, and I believe Dr. George is going to comment on that later on in this region. As a result, most flood gauges actually lost their capability to read. It started a little below 100 centimeters, 1 meter, and the 3.45 mark from 2016 was quickly exceeded. The gauges broke at about 5 meters, and the final water level height was estimated to be around 7 or 8 meters, in some regions up to 10. Consequently, the flood extent is massive, and we see here two maps from the Copernicus mapping system. The left one shows the Erftstadt and Blessem. It's along the river Erft. And here you see that famous Blessem gravel mine that I will talk about in a second. And here you see the flood region along the Ahr River, with many of the flooded areas, the destroyed houses in red and damaged houses in yellow. Now this left failure right here was heavily featured in the news, and you might have seen this. What still appears just a limited amount of damage in this photo, with damage to residential structures and this road being completely flooded away, looked substantially different from an aerial perspective. You see here this gravel mine in the very back. As a result of this gravel mine, the strong hydraulic conductivity of the gravelly soils here, the soft surface soils in the nearby agricultural fields, the water had an easy way in to fill that gravel mine as a very low-lying area. And so it formed these massive amounts of canyons here that you see on the left-hand side of the photo. At this time, these buildings were still standing shortly after they were partially ripped away, and they were not there anymore when we were there. Here we see a before-after photo, and you see it really looks like another version of the Grand Canyon. Those cuts were up to 10 meters deep. So nearby where we had, you can use this as a reference building, right, for both pictures. As a result, residential and infrastructure was damaged heavily. We can see on the left side, and also here on the top photo, the damaged pipelines. So a freshwater supply line out of concrete segments was completely damaged. Here, a massive amount to residential structures. Everything and all the debris was washed away with it. This aerial perspective again shows nicely these craters that formed in just a vast extent over this floodplain. When we arrived on site, it took a slightly different shape. The water had receded, and work and was underway to clean up the site. You can still see here some minor slope instability along the river, along the gravel mine, and we were able to access the gravel mine with police support, even though it was restricted at the time. But right adjacent to this gravel mine was also the Autobahn, A1, A61 intersection, and you can see that the Erft River, which was originally right here, and continuing here as this little stream, this is the size of the original Erft River, was able, due to just the flow velocity and intensity, to wash out and erode the subsurface layers of the Autobahn. Here you see a screenshot of a video capturing the failure of the sound barrier wall. In total, 130 kilometers of roads were closed and damaged right after. 50 kilometers were still closed and not usable 2 months later, and the initial repair cost of 100 million was by far exceeded. Along this river Erft, we had some other observations that I want to briefly mention because they were common and repetitive. as a failure pattern. We very frequently saw this erosion and washout of the area between soil, foundation, and water interface. So even though this armoring was supposed to be a little bit more engineered and stabilized as stones with cement, often we saw this being washed out, and then in severe cases causing substantial damage to the bridge foundation itself. You see this even here, this washout has magnitudes of close to up to 1 meter. Another example along the Erft River is this bridge. We looked at this also. A very common failure pattern is that washout of the abutment right here. Even though this abutment is still standing, you already see that bridge is deflecting heavily. You can see that something here on the right-hand side looks a little odd. And after checking the Google before imagery, we noticed that this abutment, while it was actually standing right here, was taken out by the floodwaters. And as a result, that pier wall on the left-hand side shifted off its original location by at least 40 centimeters and experienced substantial tilt. The Erft River also expanded substantially in width in areas that were outside the residential regions of the city. This is approximately now 3 to 4 times wider than what it used to be. You see these deep cuts here, and you see that infrastructure lines were heavily damaged. And the one thing worth mentioning here is the minimum embedment depth for those in Germany is approximately 60 centimeters. That is for areas that don't experience frost. It goes lower the more you go into colder regions. But we noticed that this might not even be enough, and this is something that could be reconsidered for future utility design and relocations, first away from riverbeds or channels, and then also considering a much lower embedment depth. From here, I want to kind of stop with the Erft River and just give a 5-minute damage observations of what we saw in the Ahr Valley itself. This was the heaviest region with damage. We visited almost every single little town and stopped at every pretty much location where there was something notable. But this was really the one that was the most shocking, and you might have seen this in the news as well. Over 200 hectares were affected. This is approximately 500 acres. Out of the 56,000 people in the Ahr Valley, 17,000 could not return into their residences. Out of the 4,200 residences or buildings, 467 were destroyed and 3,000 were damaged to the point where you could not return. Some only lost the facade, some lost the complete house, and only the basement was standing. That accumulates to 70% of 4,200 buildings had to be removed. Out of the 112 bridges that were destroyed, 60 out of the 112 bridges, 62 were completely destroyed, could not be used. 13 were severely damaged, had to be demolished afterwards, and 35 were operable after some repairs. And some of those you're going to see in the next slides. This is the entrance to the Ahr Valley as we came in when we were driving in. We, even though the Ahr Valley was closed to the public due to heavy disaster tourism, we did get the necessary permits to do our research studies there. And this is really not a lot of damage that you see here. Minor, the abutment failed, abutment region, and the bridge deck collapsed down. Compared to what we saw later, not a big deal. This is also a repair along the way. Here it's a retaining wall along the road that's being repaired with soil nailing. The original nails were too short. As a result, parts of the wall failed. It's replaced with longer soil nails, and we were able to document that as well. Coming into Schuld, the damage was much, much more severe. You can see here the river widening substantially, causing damage to the residential homes all around it, a lot of debris that flew down as well, and then also a lot of just damage to the utilities. Here you see a temporary stabilization of those electricity boxes that were exposed, but the town of Schuld really did not have electricity, gas, or fresh water for several weeks after the flood. Here you see a bridge in Schuld that is very representative of damage that we have also seen further downstream. Even if some parts of the bridges survived, the top deck was often washed off, and a lot of damage was caused by either the debris or the tree logs that were carried by the floodwaters. And one thing that all of us actually observed and really wanted to point out is that impact that those debris and tree log loading had on the bridge, not just in terms of structural impact, but also in terms of clogging the cross-sectional flow area underneath the bridge, and therefore creating a dam, holding the water back, and then the water would rise, and either that bridge would fail or it would overtop at a certain point. And eyewitness reports said to us that they experienced tsunami-like flood waves coming downstream as a mix of water, debris, and trees. This bridge was later somewhat reestablished as a pedestrian bridge and reused, and you can also see how the water masses just eroded and washed off all the armoring surface soil and vegetation around, and water levels rose here up to probably the top of the first story of those houses. If you go further south, I will skip a lot of towns right now, but one of the most severely damaged towns was Altener. You see here a double bridge that is just totally clogged and overwhelmed with debris. The bridge deck actually rotated off, the bridge foundation tilted into the ground. These bridges were still standing, but as a result, all the floodwaters were going around. The town of Altener itself was also heavily damaged, and one of these bridges also was one of the railroad tracks that used to continue here. And almost the entire set of railroad tracks or railroad infrastructure in the R Valley was gone. About 600 kilometers of tracks total destroyed in Germany, more than 1.3 billion euros in damage. Much less to railroad damage was experienced in Belgium. But we saw this over and over again. When we came to bridges that were damaged, the rail tracks were still hanging, as here in Maischoss. Here we see the same thing in Walporzheim. Here we see it towards Bad Neuenahr-Ahrweiler. And here you see that our Valley train, you know, it looks so romantic when everything is intact, and this is the situation afterwards. And this photo down here also gives us a good idea of these very common abutment failures and the washout of the abutment fill and the connection between the bridge end and the continuing natural ground or the roads. So this was often observed by us as a very weak point that requires improvement in future construction. The next photo shows a similar example. When the bridge was still standing, the abutment area was washed out. Likewise, many of the roads were washed out or eroded simply by erosion of the subsurface materials. And here are a few more examples of these. One in Belgium, this is in Bad Neuenahr-Ahrweiler. This is still not repaired today. Here in Maischoss, the erosion of the road, and this town was completely separated from everyone else, and in Hönigen. This is a photo that shows the extent of the structural damage. That's by far not the worst, but it gives you a pretty good impression of what we were able to see. Water levels often exceeded the second story of houses. They were very visible to us due to the mud line. We also noticed that lightweight infrastructure, such as those bridges, were easily lifted off because they simply rested on the abutment as a gravity kind of structure. So the flood waters, as they rose, lifted it off, and due to the velocity of the flood, pushed it to the side, as well as the debris that was carried by the flood waters. And last but not least, I wanted to show you what was immediately done to reestablish access. And this was those temporary bridges. Here you see a floating bridge installed by the military just for pedestrian access into areas that were completely cut off. And here you see one of those assembled steel truss bridges. These are also very commonly used for military deployments. And up here, this is a more long-lasting bridge that was already built later on. For the people that were removed, the government supplied these tiny houses, but especially in Bad Neuenahr-Ahrweiler and Sinzig. And so this is the temporary home until they could figure out the situation with their insurance or with what is going to happen with their houses. So from here on, I will give it to Dr. Michael George, and he is going to present two case studies, the first one being on the famous Steinbachtalsperre.
Great, thank you, Professor Lemnitzer. Appreciate that. Yes, so I'm going to talk about two specific sites we visited. The Steinbach Dam here in Germany was one of those. Most dams performed pretty well, at least that we didn't hear much about dams, with this case being the exception to experience some damage. This is a dam, rock-filled type dam. It was built about 23 meters high, built in the 1930s and later updated in the 1990s. Pretty small reservoir, but and the things you can't see in this picture really are the dam has an asphalt upstream face and an asphalt roadway on the top, and that played a big role here. Next slide. So during the event, overtopping this dam overtopped for about 3 hours, which resulted in some pretty severe erosion and gullying on the downstream side, creating some concerns for potential failure of the dam. And typically rock-filled dams don't do well in overtopping events, often failing within 15 minutes to a couple hours. And so this dam held on, and a lot of that was due to the roadway. It did have a couple outlet structures. You can see the spillway on the left abutment there, and then a low level outlet to help pass floods, but they really weren't adequate for this. Next slide. Here you can see the spillway on the left abutment. It appeared to be pretty undersized, and then partway through the event, it became clogged, which just exacerbated the overtopping. Next slide. So here's some shots. You can kind of see this is downstream of the dam. You can see the asphalt roadway on the top, and then the erosion occurring immediately downstream. And it was really this asphalt roadway which more or less slowed down the headward advance of scour occurring on the downstream face enough to really save the dam. It wasn't a bulletproof design. You could see there, oops, on the last slide, you could see pieces of that roadway falling in. And so would it have held forever? Probably not, but it was enough in this case to hold off. Next slide. Here you can see just a little bit of the materials. It was a pretty clay type rockfill material. We didn't really see much zoning even with the cut within the dam, which we'll see in a bit. But you can notice in the gullies that formed downstream, you can kind of see these steps that formed on the downstream face within the gullies, which is characteristic of a scour progression in more cohesive materials. Next slide. And a big part of this really was we used some remote sensing tools. We had a handheld LIDAR unit on an iPad, as well as we had a drone to make a structure from motion photogrammetry model. From that, and we could get some more details on some of these gullies and what the erosion looked like. And so that's up in the upper right is a cross section through one of those gullies where you can see kind of that step pool geometry. And like I said, that's characteristic of how head cuts advance in more cohesive materials. So that's good information that we can learn from. Next slide. Another component of this that I think was contributed to the dam surviving was that the crest was relatively flat. You can see the excavation they cut in after to drain the reservoir, but the flatness of the crest really prevented any major flow concentrations, such that the rills and gullies that formed were relatively even distributed along the face. And so there wasn't one big location where all the flow was really concentrated, which helped it as well. Next slide. And so here's just a picture on the left. That's at the time when we were out there. As I mentioned, they cut a notch in there. The reservoir was drained down. And then shortly after that, you can see that they installed a riprap type channel there. And I think the plan is to more or less keep this reservoir drained. I'm not exactly sure what the plans are in the long term, whether it will stay like this or if they'll plan to rebuild. But definitely some good data there that we can use to look at learning from overtopping case studies. Next slide. So the next site I want to talk about is Altenar, and specifically the Altenar tunnel. Anne mentioned this just briefly, but it's closed-in valley, so very high water levels, and this was one of the areas that received a lot of damage. Next slide. We saw that one, but you can see, I'll just point out the inlet to the tunnel kind of further down the valley there with the blue arrow. Next slide. So here's, you can see where that inlet is. You can see the blue path of the river kind of makes a big meander around it, and then the tunnel connects two of those locations on the river there. And the yellow circle there, that was about the picture of the previous slide. Here's just a close-up view again from Google Earth. You can see the two bridges coming in. And then on the other side, there's also two bridges going out. You can see a group of homes and buildings right directly downstream on the outlet of the tunnel. And then there's a wastewater treatment plant over there on the lower right. And basically all that infrastructure was damaged or destroyed or washed away. Next slide. So here's kind of a before picture of the inlet to the tunnel, and you can see there's three, so two rail tunnels and one roadway tunnel. We'll focus on the roadway tunnel there. Next slide. And then here's after the events, you can see the damage to the two railroad bridges. The pier on one of the bridges in the forefront is sunken down from scour. And then also note the building in the upper left corner. You can see the water line in that, which will be shown in the next picture. So here you can see there's that building. The water level was well into the second story, so flow depths approximately 3 to 4 meters. The inlet to the roadway tunnel, which received water during the event, is kind of hidden behind those two bridges, but you can see the tunnel invert is right along that white dashed line in the picture on the left. And then also just wanted to note the steeply dipping bedrock in the background there. That'll be seen on the other side. Next slide. So here's the entrance to that tunnel. You could see some of the debris marks along the lining of the tunnel. We also saw some plucking of the concrete blocks in the pedestrian path through the tunnel. Those were really covering some of the utilities that went through the tunnel. And I think because they had those gaps underneath, that allowed the pressures to get underneath those slabs and essentially pluck them out and mobilize them downstream. Next slide. As I mentioned, so the flow in the event went through the tunnel, and that wasn't actually a first occurrence for this particular case here. You can see the prior to the 21 events, this tunnel flowed through in 2016 with a depth of about 30 centimeters. But you can see over there on the right, the depth was a lot higher, or at least what we thought was the water depth was a lot higher, about 3.4 to 3.8 meters there. The discharge associated with this event was some estimated to be similar to the 1910 event, which you could see the water level in the tunnel then was about the height of my head. So it really wasn't clear what the discrepancy in the potential water levels were or was, but based on what we saw, this appeared to be much higher in this event. Next slide. And so here's the tunnel exit. You can see in the upper left some of the building infrastructure up there and the roadway that comes down and around. And then in the lower right, the picture, you can kind of see the lone car in the parking lot there. Behind that is essentially the natural river path for the R. Next slide. So here's a couple of pictures from the 2016 event. On the left is the inlet to the tunnel, and then on the right is the two railway bridges. Next slide. And then here's the outlets. You can see water is essentially just cascading down the roadway there, and it wasn't a significant amount of damage in 2016. Next slide. The 2021 events was quite a different story, actually. And so you can see kind of the massive scour that occurred right at this outlet. You can see the exposed bedrock there and the steeply dipping bedding planes or foliation, and then all the undermining of the houses on the right there. And it's not surprising if you consider, 3 to 4 meter thick hydraulic jet coming out of the tunnel and impinging down on the material below that we get such significant erosion. Next slide. So here's just a quick slide. I mentioned some of the bedrock. Those outcrops held up pretty well. We did notice some plucking of some of the blocks. There's looked to be more favorable jointing orientations, which I think helped resist some of the erosion. It did look like there was kind of a shear zone or a weaker zone kind of running down the middle between those two bedrock outcrops, where we saw more scour and coincidentally the undermining of the white retaining wall on the side there. But basically those hardened areas of the bedrock kind of force flow to the right of the photo towards these more pluvial type soils, which eroded quite readily, and hence all the undermining on that side. Next slide. Here's another view just downstream. You can see the two bridges for the railways coming out there. On the right abutment, they had quite severe scour there. The wastewater treatment plant at the top of the screen that was essentially destroyed during the event. Next slide. And this is a case where we used both drone and a ground-based LIDAR. We only really had about 30 minutes to get into this site. And so having those two methods to collect this data was quite helpful. I think I took about 5 manual strike and dip measurements on the outcrop, but with the LIDAR data, we can go back and take hundreds or so in the office. So that was a real advantage having that equipment with us here. Next slide. And here's just kind of a quick slide showing what's happened with repairs slightly after. You can see some of the railway bridges on the upstream side were being demolished. The roadway was being rebuilt, and then on the tunnel exits, just a couple months after we were there, they had that area filled in and a roadway being constructed, and now there's a full roadway there that connects in with the rest of the highway. And I think that might be my last one, so I'll hand it over to Professor Gardner.
Great, thank you very much, Mike. So I'll be talking a bit more about some of the instrumentation we use for phase 1, and then going into a bit more detail about some of the multi-spec stuff. So next slide. So the first equipment type we use is LIDAR, light detection and ranging, which uses pulsing laser to measure ranges. First sensor we used is a Leica RTC 360 scanner, and that has a range of about 60 meters. You can see it in that center image there, sitting on top of the tripod. And so that unit, along with a tripod, batteries, and iPad, all fit inside a backpack. It's relatively lightweight, so really good for rapid post-disaster reconnaissance. It also does relatively quick scans. You can see an example of a structure that we scanned there. This is a bridge in Trews, Belgium. And clearly there's some settlement and tilting in the piers. And if you look at the bottom image on the right there, you'll see this is the resulting 3-dimensional model that you get out of the LIDAR. And you can make really accurate measurements in the LIDAR. So assuming that that bridge pier was initially vertical, you can look at the amount of tilt, and then also looking at the pre-flood bridge deck elevation, you can get a sense of how much the center of the bridge settled, likely due to scour of the foundation underlying that pier. Secondly, we used an iPad Pro with the onboard laser scanner. This was a relatively new thing that just came out with the recent iPads, and you can see an example of that on the left-hand side there on the bottom left, kind of like what Mike had talked about earlier with his example from Steinbach. This was an outlet from the city walls in Buckminster Eiffel. And what's really great about the iPad with LIDAR is that you can scan these relatively smaller features quickly, and you can also get really good coverage compared to a conventional terrestrial LIDAR scanner where you'd have to set up multiple scans to get enough coverage and avoid holes. With the iPad, as you're walking, you can kind of see where holes are, you can scan those, so you get a really nice 3D model of some of these smaller features. Next slide. Second, we also used unmanned aerial vehicle imagery. We collected manual images where we were just flying the drones around, snapping photos, and also taking videos. Additionally, we flew gridded flights, double gridded flights to create 3D models, kind of like what you see on the right-hand side here in this image. This is actually a three-dimensional model created using structure for motion, where we get a point cloud similar to what you might get out of LIDAR, but you get more coverage, less blind spots, albeit with less accuracy. The types of drones we flew on this first deployment were smaller drones, so DJI Mavic 2 Pro, you can see like on the left-hand side there, and those arms actually fold in. So again, this is a small piece of equipment. You can throw it in a backpack. You have high mobility with it. And one of the things with the drones, kind of like what you can see in a 3D model on the right, is that often with post-disaster reconnaissance, you don't have access to everywhere. So like walking down in that debris field would not be safe, nor walking on those scarps from the head cutting. So deploying the drone so you can get a better view and access some of these areas that otherwise aren't accessible is really a great feature. Next slide. So last piece of equipment I'll be talking about, I guess, collection techniques is terrestrial multispectral imagery. The sensor we deployed is a MicaSense Ultim. You can see that on the left-hand side there. And those 5 lenses that kind of look like spider eyes, those are electro-optical cameras, and they all trigger simultaneously, and they each sample a different band in the light spectrum. So you can look at different reflectance characteristics of materials and ideally identify perhaps some features or different responses. Additionally, in that image on the left-hand side, you see those 2 smaller circular features on the top and bottom, and those are actually thermal cameras, so you can get also thermal imagery to match with that. And then on the right-hand side, there we're collecting images in Germany. On the right-hand side, you can see Nina holding the camera, and then I'm holding a battery pack, and I'll tell you a bit more about that. But this is really an experimental deployment. The use of multispectral imagery and this type of post-disaster reconnaissance hadn't really happened before, or at least to our knowledge hasn't really been done. So looking a bit closer at this image here, you can see there's the camera being held. Normally, these types of units are mounted on a drone. They're used a lot in agricultural deployments for monitoring crop health and that kind of thing. But in this case, since we were just carrying it, we had to power it externally. And so that's what that blue wire there represents, is we're just powering from that external battery pack. Additionally, normally the camera is triggered by the drone by connecting to its to the camera's Wi-Fi. In this case, we connected to that with a cell phone and then just triggered pictures or collected images by pinging the Wi-Fi. Next slide. So interpreting multispectral imagery, what we're looking at here, so I'll kind of walk you through this in this case study for Bergischerhof near Maischoss. The image on the left is just a standard, RGB type image. And both the RGB images and the multi-spec images were taken about 3 to 4 weeks after flooding. The visually identified high water mark when we were out there is in that structure on the left. If you look in that image on the left, is just below the second story there. If you then look at the images on the right-hand side, those are those 6 different images that are collected simultaneously by the multispectral camera with these different color bands. And what they show is the reflectance in each of these bands. So the top left one is sampling the blue band, top right is the green band, middle left is red, middle right is near infrared, and then bottom left is red edge. And then that lower resolution image on the bottom right is the thermal imagery. So we're looking at reflectance in these different bands. And so you can see that the high water mark based on what we observed in the field, also manifests with different levels of strength in the multispectral imagery. So we wanted to look a bit more if there's a way to isolate the signal to potentially use this in future applications. Next slide. So what we're looking at here is what we're trying to do is take different combinations of these reflectances and see if we can isolate the signal associated with the high water mark. And what we've done here is on a pixel by pixel basis in each image, we've taken the difference between the reflectance in the red edge band and the blue band and just looked at what are the pixel by pixel values and plotted a histogram of that. And so you can see it's separated into these three modes where the first mode is represented by that image on the bottom left, which is associated with pixels containing the sky. Mode 2 is associated with pixels that are in the doorways and reflectances from windows, and then also some of the concrete on the lower portion of the image. And then mode 3 on the right there, on the bottom right, you'll see most of the pixels there are associated with the building facade. And you can also see a difference in the index values for pixels that are above and below the waterline. So we wanted to see if we could isolate those a bit better. Next slide. So here what we've done is just to isolate those pixels, we're filtering in two ways. The first way is if you look at the top left there, this image shows here what we've calculated is the normalized difference vegetation index. And so for the NDVI, pixels usually, or the index value generally greater than 0.2 indicates vegetation. So we wanted to eliminate vegetation. So we filtered out all pixels that have a NDVI greater than 0.2, which is represented by those yellow pixels there. Second, if you look at the top right image, that is a thermal overlay on the building facade. And you can see that the temperature generally is higher on the building facade for portions of the building that were above the high water mark versus below. You can also see the temperature in the concrete is substantially higher. And so what we did is we filtered also based on temperature. So any pixels with a temperature value greater than 27 degrees were also filtered out. And then the result of that filtering is shown in the bottom image there, where you can see we've isolated pixels associated with the high water mark there. Next slide. So what we tried to do then additionally is see if we can isolate this signal to a single mode by coming up with different combinations. And so what we've done here is we've still kept that pixel by pixel difference between the red edge and blue reflectance, but then we've normalized by the sum of those two bands. And then what ends up happening is those different modes get collapsed into a single mode that now isolates pixels only associated with being below the high water mark. If you look at that image on the right-hand side, we're plotting that NDREB, and you can see that it does a pretty good job at isolating the pixels below the high water mark. So we could potentially apply this approach to automatically map high water marks using multispectral imagery, whether it's terrestrial or we mount it on a drone and access areas that we couldn't necessarily get to by foot. One thing to note, though, is near the roof line there, you can see there's some noise there, and that's associated with shadows. So there's still some work to be done here, but you can read more about this in this manuscript that hopefully will be published soon. And so this should transition well to what Nina's going to talk about in terms of using different measurement techniques to try and get a more comprehensive idea of how things unfolded.
Thanks, Mike. So you've seen we have collected in phase 1 a lot of data, a lot of observation already. So why come back for a phase 2? So even though we were able to collect so much data, there were clearly access limitations in August 2021. Some of that due to water levels and flow velocities. In the images, you saw that the waters had obviously already significantly receded. However, there was still a lot of unknowns. There was water access was impossible in a lot of places. And just there was a lot of ongoing rescue and first responder efforts still going on. So that did not really allow a more in-depth data collection there with regard to, in particular, in the water. And so you saw a lot of examples where scour has been mentioned, in particular piles that even with the water has receded is still sitting in the water. So from the changes to the structure, we can we can make a pretty good assessment that probably scour is responsible for it. But if you really want to understand the role of the water soil infrastructure interaction and possibly also debris interaction, it would be great if we actually have a better idea how deep is the scour hole, how big is it? So what are the erosion patterns around the infrastructure? What are possible deposition patterns, right? Where's the sediment ending up? And what are the geotech properties actually in the water, and how does it relate to these erosion and deposition patterns? So here on this figure, you see the case study that I will talk about a little bit. So that's the pink pedestrian bridge. That's what we called it in my shows. It's actually really close to that building that Mike just showed. And you see here on the right-hand side, I kind of highlighted that there's a lot of different soils from fine to really gravelly there. That is obvious. You may also say, hey, this deposition layer that you're seeing there looks pretty fresh. So probably that's also fresh deposition, but we're already a little bit less sure about that. However, if you look at this arrow towards the bridge, how could we tell how deep the scour hole is? Is it a meter? Because typically the water depth here is like maybe 0.5 meters, or is it much deeper? We don't have really a good idea without looking into that. And that was actually a purpose here, to come back, collect for a few specific sites, in-depth data that allows us to really investigate in detail this soil infrastructure water interaction. Next slide, please. So we brought quite a heavy load of equipment out of there. So terrestrially, we did soil sampling, we did in situ testing for classification and characterization of the soils. You have already heard about the UAV-based multispectral imaging for land coverage, mapping and DEMs. We brought that back. We also brought the LIDAR back. We did look into some synthetic aperture satellite images. However, in some sites that were effective, at this site specifically, they were not so effective because the valley is so steep that there's a lot of shadowing going on. We also, and this was what we could not really do during the initial phase, we did quite a bit of the subaquatic work, so work in the water. So we also did here soil sampling and in situ testing. We collected bathymetry, so detailed water depths from a single beam sonar that was attached to a remotely operated vehicle, the Z-boat, that was operated and provided by the Rapid facility. And we did, where that it was too shallow to deploy the Z-boat, we did RTK surveying, but the Z-boat actually helped, in particular in places like these. If you look again at the picture in the background, this kind of murky green water could be anything, could be wadeable, could be meter steep. Then we brought out a side scan sonar that does riverbed imaging. So hopefully gives, the idea was to give us an image of, for example, infrastructure hanging in the water, bridge piers, and how they look underwater. And then we brought out a chirp sonar, where the goal is with lower frequencies to actually scan into the seabed to think about things like infill of scour holes, seeing new deposition. So the idea was, in summary, to get a seamless topographic and soil mapping and characterization of the riverbed, riverbanks, and surrounding areas and around the impacted infrastructure. Next slide, please. So during phase 2, I think it was already mentioned, so this occurred in March, April 2022. We had 7 US-based GEER team members on board, and again, collaborators from Germany that actually helped facilitating this work, significantly also considering all this equipment we had to ship and prepare and so on. We chose 5 sites, and those are mapped on the top right here. The pink pedestrian bridge near Maischows that I will talk about most and that you saw in the previous images. The bridge near the Zum Sänger Hotel in Dernau, that's what you see on the bottom left there. You see that the abutments and the piers are still standing, but the bridge is completely gone. We worked at the R Bridge in Liers, that's the one you see on the right bottom hand side. And we worked at the double bridge in Altena that was mentioned before. And we also looked at the R-Rhine confluence, where also one bridge was completely swept away. However, we would also see these really significant erosion scarps that you see in the bottom center image here. These 5 sites featured aspects of that they're at least on the water, near the water. Not much repair work had been done around the areas and structures that we were most interested in. We had good access there for equipment. And so that's how, after considering about 10, 12 sites, we narrowed it down to these 5. Okay, next slide, please. So here's some action pictures. And again, now I'm going back to this case study from the Pink Bridge in my shows. So you see on the top left, this is the Z-boat, this remotely operated vehicle right now, supported by one of the rapid facility surveyors in this location in my shows. So this was really essential to collect bathymetric data here because we were absolutely unsure what kind of water depths to expect. You have on the center top, you have one of the GEER team members deploy a portable freefall penetrometer. I have a zoom on this a little bit later on. So this is practically a measurement of strength in the seabed. And we use this little dinghy for this. And these little inflatable hard bottom dinghies are actually quite helpful in an environment like this. You can just lift them into the water. They're quite resilient when it comes to scratching on it. And they allow you to navigate in these fairly now calm waters quite well. And then you have on the top right, actually, we also use the dinghy to shuttle people around. You actually see Elliot, who gave the introduction in the very beginning with the LIDAR, and we used here the dinghy also to move the LIDAR from one side to the other. On the bottom left, you see how we actually deployed one of the sonars, also from the dinghy with a person sitting practically with a laptop in the lab. And on the very back of the boat, this little metal structure you see, that's actually the cage that holds the sonar. And then I have, just as a reminder, added here one image of when the flood was, or shortly after the flood event, when water was still high, and just giving you the, like an idea of why it was so impossible to actually get the measurements there. It would have been far too risky to work in this. Okay, next slide, please. Okay, let's look at some example data. So here's some data from this portable freefall penetrometer. So compared to more traditional methods, the advantage is that it's really small, it's very rugged. You can just use it here from the dinghy compared to coming with, for example, a heavier cone penetration test that could go into the water. And we get still, even though it's a simple and a little bit more basic device, we get quite important information that we are interested in. So in these graphs, you only see the measurement of deceleration. That's what it measures. And from that, we then can calculate towards strength measures like undrained shear strength for cohesive soils. But you can also get a really good idea of actually layering. What in particular is here a target. It doesn't penetrate that deep. However, if you're interested in erosion, deposition, surface processes, that may not be the biggest problem here. And if you're looking at the left-hand side plot here, for example, you see very clearly this like soft, very non-resistant layer on top of the gravel layer that then practically stops the probe on the spot. So then from, again, the penetrometer results, you can calculate an undrained shear strength that came out about 2 kilopascals, slightly under for this top layer, the soft top layer, and that actually compared well to lab tests that we then performed on samples. On the right-hand side, still the same area here, that Maisha's Pink Bridge area, you have still this really soft layer on top, but a little bit thinner, and then you have more of an intermix layer where there seemed to have been a little bit more of turbulence and mixing of the mud deposits with gravel before you hit this gravel layer then. So those are information that give you an idea of particular deposition layers, but also if you find really just hard surfaces, often that gives you an idea that those are areas where erosion occurred because everything that is looser or softer is actually moved away. Next slide, please. So this is an example of data collected by the Z-boat combined actually with the terrestrial DEM obtained from the LIDAR data. And so this is something that I really want to highlight. Is very, very cool and actually quite unique. That you have the bathymetry from in the water. Those are the little scribble lines. I know they look a little bit chaotic, but I actually prefer to show them here over a triangulated interpretation. So here you actually see the tracks of the Z-boat, and I hope you also recognize the effort that here the team put in collecting all of these lines. And you see the hot colors is actually shallower water, about 0.5 meter deep. And when it gets to these cool colors, you're actually getting to depths of 3 meters. And that's something that I actually really want to highlight. So we are seeing this scour hole of down to 3 meters in a water body that typically has an average water depth of 0.5 meter to 1 meter, evolving around this destroyed infrastructure. And we have actually a second spot that is deeper if you're just coming around the curve. So this is actually essential data if we now want to go back and actually model how erosion and deposition occurred here, how the scour occurred here. This is really essential data to make sure that we are validating the model and get the processes right, and then therefore understand in detail what actually happened. And I do want to highlight here this combination with a terrestrial LIDAR offers like a full picture, in particular in a place like this where flooding is not only in the riverbed and it attacked the bridge, but actually went all the way up onto the banks. So that allows us to get this kind of seamless connection of bathymetry to topography to get a really good idea of how sediments were eroded and deposited, and also scour again occurred. Next slide, please. So this is, I understand this looks a little wild, and it may remind you going to the doctor and getting an ultrasound of your knee, and it's practically exactly how this works. So what you see on the left-hand side is a low frequency chirp sonar image pinging at about 8 to 12 kilohertz, and it's actually pinging into the ground. What you're seeing here, this little V shape in the image, is actually the scour hole. And so now you may say, well, I mean, we can already map out the scour hole from the single beam sonar that the Z-boat provided, and that is correct with regard to depth. However, what this gives us, in particular, if we work a little bit more on the data on filtering, you may notice that actually these walls or the surfaces of the scour hole actually vary in shading. We have on the left-hand side a little stronger brightness. We have a little bit more washing out on the bottom and a little bit less bright on the right-hand side. And so this is typically indicative of different soil properties. And we're trying specifically to hunt down if this, in the bottom of the hole, there's a little bit washed out area, if we can relate this to infill of scour after the water flows receded. And that is actually a problem that, for example, Jean-Louis Briot has pointed out for quite a while when it comes to scour, that if we are coming back after the flood is over, scour holes infill again. So this may be an opportunity to actually tackle this problem and get an idea of how much has been infilled after the flood event and what was the original depth of the scour hole during the flood event. On the right-hand side, you see the side scan sonar image. So that's practically an image of the seabed. And for example, on the bottom, the little spike or triangle you see is in this case actually a bridge pier that we are seeing. We see also how the edges are practically a little bit scratched up in some places. And we do see a lot of cobbles around it. And then you have this darker area around the tip that is actually then related again to scour. So that helps us to map out the scour around a piece of infrastructure and also look at infrastructure damage and potential debris that is still there. I could not place an image here from the debris off that bridge deck because of all the cables. That looks even a little bit wilder. However, we can actually see the cables and the different elements. And so that helps really a lot with understanding this interaction there. Okay, next slide, please. So we also worked a little bit more on multispec. I will keep that short. Mike talked already a little bit about multispec. So what we've been trying here together with Mike and some measurements that we also did here in the lab at Virginia Tech. So we took soil samples and photographed them again with a multispec at different densities and different moisture contents. And then we also actually tested the reflectance using a spectrometer and getting what you see here on the bottom, practically your spectral signature of that material at that density with this moisture content. And you see on the top right, then multispec data that is obtained from the drone. Here, the iron oxide ratio already gives you some good mapping of different properties and land coverage and soil. And we are hoping that if we can calibrate that further with the lab measurements, that we could even get a better idea of, for example, moisture contents in those different soils and these material changes, and compare that to changes prior to the flood. Next slide, please. So just in summary for phase 2, so we collected really 5 unique terrestrial to subaquatic data sets that included bathymetric and topographic change in this location, sediment relocation, soil properties and conditions, and really giving an idea of flow sediment structure interaction. I would also like to point out that we tested here combinations of methods for post-flood reconnaissance that have not been really used in this way and in this combination in a setting like the one we are addressing here, including like remotely operated surface vehicles with unmanned aerial vehicles, low and high frequency acoustics in a shallow water body. That's really just more recent technology that allows us to work with these instruments here. And then subaquatic acoustics and multispectral aerial mapping that is then combined with the in situ testing for mapping the soil type and properties. And that's all I have, and I hand it back to Anna here.
Thank you very much. We just want to use the last 2 minutes to summarize some of the selected key takeaways that stood out to all of us as team members. And that is based on phase 1 and phase 2 observations. One was really what I already mentioned, was the debris mobilization, either natural debris or man-made debris. And it really played a significant role in failure of many bridges and other infrastructure elements. It's often not accounted for in the hydraulic design and also not in structural design codes. I can only speak for Germany. I know Switzerland has included these type of analysis, but it is time to really make this a an important chapter, as this type of failures due to the frequency of this natural hazards loading will increase. The weak points were often located at the soil foundation interface, either observed as washed out abutments or erosion of the armoring regions, particularly to bridge infrastructures. The utility infrastructures, as I mentioned, was in almost all cases exposed. We didn't even show you photos of Bad Münstereifel and entire roads and streets washed out, and everything was pretty much laid open. A deeper embedment could be considered, and a better structural connection or embedment would be beneficial in the future. Overtopping of the embankment dams more often leads to failure. In our case of the Steinbachtalsperre, the presence of the hardened asphalt roadway really saved the dam from failure, as Mike pointed out. We also all agreed that the combination of the emerging remote sensing and geoacoustic tools that we were able to use, combined with the geotechnical testing, really enabled unique insights into flood soil infrastructure interaction. We were able to collect a very large amount of data quickly, and we'll show you where to access them publicly. And especially this was useful in locations where we didn't have enough time, where we were given only 20-30 minutes, or where we couldn't even go and pretty much had to fly in later. The handheld LIDAR was very useful as a small portable tool for documenting conditions quickly and accurately in 3D. And this is something that we thought would be very beneficial for any group that deploys to take advantage of that technology that's now commercially available. And I want to point out again what Nina already mentioned. Within our phase 2 and also phase 1, we really assembled comprehensive post-flood data sets, more in-depth measurements at 5 distinct locations that now enable us to do a lot of follow-up analysis on flood soil structure interaction. With that, I would like to show you where you can get access to these publications. Our GEER report, as Elliot mentioned, it's pretty hefty. It includes 260 pages and covers much more area than what we presented in this webinar. We have soon a report coming out that summarizes the phase 2 deployment from March 2022. The first data set is already publicly available. That includes all data measurements, including LIDAR, SFM, and regular photography from phase 1. You can access that through Design Safe. And we will also publish everything from phase 2 and make the DOI available very shortly. Again, we would like to acknowledge our funding agencies. We're very grateful to GEER and the National Science Foundations for making this 2-part effort possible. We would also like to thank the NSF program manager again for facilitating an NSF rapid deployment as phase 2 with a separate funding amount that enabled this collection of high quality data. One of our team members from the Dutch team actually created an outreach video that you can access on YouTube. It is in Dutch and in English. You can see an excerpt here on the right-hand side. It's ideal and highlights for young people, I would say maybe 8th grade through the end of high school, as well as the beginning of college, gives an idea of flood damage, flood engineering, hazard engineering as a interesting feature to entice students to pursue engineering and become interested in it. This is our heavy list of publications. Whatever you see here on those conferences, they are either accepted or in preparation, and most of them are already published. It was very well received to present this work nationally and internationally. We have 2 journal publications that have been published or accepted, and we're currently working on 8 more. One of them is actually a 3-paper contribution to special issues led in collaboration with our German collaborators and the project that they have there in Germany. With this, we are at the end of our webinar. I'd like to thank my team again for preparing the slides, for going on those trips, and for doing great research and having a lot of fun together. And I would like to thank the audience for sticking this out with us, and we will stay around here to answer some remaining questions. And I believe Elliot might have collected some questions at this point that came in through the chat, and I would just like to invite all speakers to come back on, and I will stop sharing, and maybe we can address a few of those questions. Thank you.
Yep, so we do have a few questions in the chat. I do want to say that this recording is going to be available. We'll post it to the GEER YouTube page, and we will post it to the GEER website. There will be a few other webinars in the next coming months about different deployments and GEER tools and technologies. In the following emails, we'll probably include a link to this recording, so you'll be able to find it in a number of spots. We have a few questions here. I think Nina is typing one right now, so I'm going to skip to the next one. Kamal says, thank you for the great informative presentation. When collecting data from the water body, how do you make sure to not disturb the data, such as velocity?
I guess this is also directed at me. So so maybe I just answer the first question now that I'm talking. So this is on the side scan sonar image and the round morphology there, and I totally agree. Yeah, it looks a lot like erosion from persistent eddy there. How often do we see this? Actually, not often, but the reason for that is more that we actually don't have that much data of this type yet. So I'm hoping that applying these methods in this combination more will actually hopefully answer this question, how often we are seeing this. We have not, so the other location where we may see this is actually the 2 other bridges, the one in Lies and the other one at the Sumsänger in Dernau. So they also show this round erosion pattern in the side scan sonar. So at those 2 locations, it seems that we are seeing something similar. But otherwise, again, like we rarely get data of such a severe event and then actually have the option to look into the water like we did here. So I don't have a good answer of how often we are seeing that here. But hopefully we get more of these data in the future. On the second question on the velocity, so if I understand the question right here, so I assume this is related to moving around on the water and paddling around and hopefully not disturbing things there. But so there the advantage is truly in this shallow water, if you're actually in just like this dinghy that you're carefully paddling around. I'm sure that here my team members can actually confirm that we did not stir up much sediment. We did not do active flow velocity measurements here because obviously the flood was over at this time, so there would be more the water gauges that were in place, and most of them failed actually at some point. But during the measurements in the water, by using actually the Z boat that is really light and small, and by using a small dinghy, we really avoided any interaction with the soil and changing potential morphologies or soil properties. I hope I understood this question right. Otherwise, just type again into the chat and I'm happy to answer there.
So we actually have one more sonar question, which is, have we been able to compare any of those scour geometries from the ZEBA or from other field measurements and compare them to numerical models?
Not yet, working on it, hopefully soon. So we are currently actually cleaning up the sonar data. As I mentioned, that's also the reason why on the side scan and chirp I presented still a bit rough images. So we're actually now working through different filter processes to clean that up. And then that is absolutely the plan, to actually use such data to feed it into numerical models and then validate them first and then understand how these events happen and interact with the infrastructure. Thanks.
We have another question from Kamal, who asks, do you believe there's enough data to improve design codes to account for debris mobilization?
That is a tricky question. And at this point, what we are trying to do is using some of the bridge data and settings to reconfigure that numerically and perhaps be able to simulate it. The difficulty is that is a wide assumption of flow velocity since gauges broke and exact data are not available. But as a guideline, as I mentioned before, Switzerland has several guidelines and a lot of publications that have developed preliminary and also advanced models on how to account for debris and tree log impact loading on bridges and how to properly design for it. And I have looked for that in Germany and Belgium, and I have not found it yet. But I believe following this flood, this is definitely something that we and in collaboration with our German colleagues can work on. So for now, our modeling would be preliminary based on observations and bridge data that we have, but obviously collaborations and maybe more data are needed to make this into a solid design code change. And I believe I answered the other question remotely about the return period, so it will be in the answers to the chat.
We have another question that is wondering about any analytical methods that might be out there to determine max scour depth under harsh flooding conditions.
Maybe I take a first step and others can chip in. So yeah, absolutely. There's quite a number. But even the analytical methods, they're often either laboratory based or they're based on a large assembly of field observations. But considering an extreme event like this on this level with these water levels, I think Anna showed and also Mike showed very clearly how far above this was in this tiny narrow valley that is so extremely developed. I think that is something that we have very few data sets of this, as well as very few laboratory studies would actually reflect conditions like this. So yes, there's a wide range of analytical methods. I think it will be interesting to see actually which ones of those also perform well for a scenario like this. Overall, a lot of them, when developed, were probably not really developed for this combination of settings or cover practically all conditions as we experienced here.
Okay, I think that's it for the questions. If you have anything else, put it in the chat and we can try to answer it here at the very end. But otherwise, I think we are a little bit over time and going to wrap up here. Again, you can find the recording of this on the GEER website at geerassociation.org. We'll send out an email with the link and put it on our YouTube channel as well. So any of those three sites, you can try to find the recording if you want to go back and listen to this or look at some slides. So we thank you very much for coming and joining with us today. And you can catch us at our next webinar, which will be covering the Taiwan earthquake from earlier this year. And you can look at your email for an announcement for that soon. All right. Thank you very much, everyone, and see you later.